Hello. Okay. Let's do some math today, huh? We are in our integral unit still. We're doing the integrals of transcendental functions, which I might not have used that word before in the past, but transcendental pretty much means your trig functions, your exponential functions, your natural log functions, those types of functions. Okay. So we're going to give a lesson to that today and add that to our list of shortcut rules. I got a warm up here. This is actually a free response from back in the day, and I don't have the year. I can easily Google it, but this is a free response from a few years ago that actually I'm going to do in class with y'all. All right. I think I'll be able to get through the entire notes today in under 30 minutes. So I think leaving number 3 here will be good for us to do in class. All right. So let's go ahead and jump into it. We'll know some rules today. Learn some integration rules. Those first two we kind of already talked about. We already know those. So we'll go ahead and write those down. We know that the integral of 1 over x is just the ln absolute value of x plus c. And it's absolute value because we're allowed to have negative values in this function, but we can't have negative values in the ln function. So we restrict the domain by saying absolute value of x. We know the integral of e to the x is just e to the x plus c. All right, so the integral of a to the x, working backwards from a to the x, is a to the x multiplied by 1 over ln of a plus c. The reason we have that 1 over ln of a is because if you take the derivative of a to the x, remember that you have ln of a, we have that 1 over ln of a to cross that out. So you'd be left with a to the x. So memorize that. And we know the integration of sine and cosine. That's just doing that, this is just working backwards. We're pretty good at that. But the integral of tan of x is the ln absolute value of secant x plus c. Now, I know that seems really random, but let me take a second and explain where that comes from. And it's not too terrible to prove that or to show that. What if we write the integral of tan of x as the integral of sine of x over cosine of x? Okay. Well, turns out you can solve this integral doing u substitution. Now, honestly, you can let u be, I don't want to say either one. The best bet to let u be would be cosine. All right, here's why. If I let u be cosine of x, then du is negative sine of x. Okay? So, or dx, I forgot the dx, sorry. So the negative comes over. All right, so we got negative integral, and the sine of dx substitutes out as du, and the cosine of x substitutes out to u. So what I'm left with is 1 over u du. Okay? And then, so what I'm left with after that is negative, the integral of 1 over u is the ln absolute value of u plus c. And plugging back in for u, we have the ln absolute value of cosine of x plus c. Now, I realize that this does not look like the one I just wrote down. In fact, I think the book might even have that bottom part as the identity, but the more agreed upon, the nicer identity is they actually bring this negative up into the natural log, doing power logs for natural logs. So really you can say cosine to the negative first of x, which is 1 over cosine. So we can really say ln absolute value of 1 over cosine x plus c, and 1 over cosine of x is just the same thing as secant of x. Okay, so just FYI, that's where the integral of tan comes from. It's the ln absolute value of secant of x plus c. We don't do it. We don't use those as much, but it's helpful to kind of have it noted and have it written down. Okay. All right, let's look at an example. Example 1 here. The integral of 3x minus 1 over 9 minus 2x plus 3x. Well, if I'm integrating that, I'm sure you're probably thinking, all right, let's try some u sub. So you have some options here. And my suggestion is to pick the more complicated or the higher power. I'm going to do 9 minus 2x plus 3x squared as u. And so du is negative 2 plus 6x. Okay. Or if I want a dx, sorry. Or if I want to kind of rearrange that, that's 6x minus 2 dx. Okay. Well, it's not quite the 3x minus 1 dx, but we can easily adjust it to look like that. Like, what if I take the GCF of 2 out? Do I not have 3x dx and 3x dx? So I can make this du, and I can bring the 2 over to the other side as a 1/2. So what I'm left with is 1/2 the integral of 1 over u du. This is u, that top part becomes du. Okay. And so this brings into our new rule, the integration of 1 over u is the ln absolute value of u. So we got 1/2 ln absolute value of u, which I'm going to go ahead and say is 9 minus 2x plus 3x squared plus c. Now we use u sub in this problem, and just another thing that I want you to kind of be aware of. If we have a rational with two polynomials, one with a degree of 2 on bottom and a degree of 1 on top, remember what I said, if they differ in degrees by a power of 1 from bottom to top, then you're going to be taking the, you're going to be doing u sub of L. Okay. All right, let's do a few more examples. 2 to the x over 2x plus 1. Well, let's try some u sub again. Top or bottom, which one do you think you're going to let be u? Well, top. Or, I'm sorry, the bottom, because it is a little bit more involved. It's a little bit more complex. But if you take the derivative, okay, du is equal to, what's the derivative of 2 to the x? Let's take it back a little bit. Remember, the derivative of 2 to the x is 2 to the x times the ln of 2. All right, remember, it's if you had a to the x, it's a to the x times ln of a, and that's the derivative. Okay. All right, so we got the 2x dx, we got the 2 to the x and the dx. Let's bring ln of 2 over to the other side. So I got 1 over ln of 2 du equals 2x dx. So like I have that, I can substitute out for du. And I'll just go ahead and bring the 1 over ln of 2, that constant on the outside of the integral. So 2 to the x dx is du, and I'll let the bottom be u. And so the integration is going to be 1 over ln of 2, ln absolute value of u, which in this case was 2 to the x plus 1. All right, maybe try 3 on your own, but I'll go ahead and go through with it. Tan of 3x. So I'm going to let u be 3x and du be 3 dx. And so we have 1/3 du is equal to dx. Okay. So I'm going to bring the 1/3 out. I'm left with the integral of tan of u now, du. And we're going to get to the point in the future where we're doing the sine, tan, cosine of a constant x so much so that we're never like we're going to get to the point where doing u sub is going to be kind of like useless, because you're going to see a pattern that the 3 comes out as a 1/3. It's just that's how u sub works with a constant times x. But we're not quite there yet, I guess. All right, the integral of tan of u, well, is the ln, absolute value of secant of u, which in this case is 3x. Very nice. All right, example 4. Example 4 is a definite integral, so you better believe I'm going to be doing some u-bounds. I love my u-bounds. All right, well, it looks kind of crazy, but it looks like the inner function here is x squared plus 7. which makes du 2x dx. Okay. Well, I have the x dx, I have the x and the dx, so I'm going to bring the 2 out as a 1/2. So what I got is 1/2 integral of x and dx go away as du, and instead of 10 to the x squared plus 7, I have 10 to the u. Now, I don't want to go back to x, so I'm going to change my integral. Instead of 1 to 2, I'm going to change that using my u equation. I'm going to have 1 squared plus 7, and I'm going to have 2 squared plus 7. 11. So this is the same thing as 8 to 11. Okay. So now I can ignore everything above this line and just integrate this problem. So what we have is 1/2. The integral of 10 to the u, okay, remember the rule. The rule is 10 to the u times 1 over ln of 10. Okay. And we're evaluating that from 8 to 11. All right, and usually when I'm doing definite integrals, I like to bring the constants out before I plug in the numbers. So like I'm going to combine 1/2. I'm going to go ahead and bring that out as 1 over 2 ln of 10. Okay. And then I'm going to do 10 to the 11th minus 10 to the 8th. And honestly, I don't want to, I'm just going to leave it this way. That's as simplified as we need to go. Okay. All right. So we learned how to do it with a to the x, e to the x, ln of x, tan of x. We're learning all these transcendental intervals. All right, a couple more integrals. Now, these last two surprisingly show up all the time, especially when we get to applications. I'll make sure we're good on this. We have seen both of these before. When we take the derivative, we get these, right? So if I take the integral, right, what do I have to take the derivative of to get this first quantity? Hopefully you're racking your brain and you remember that the derivative of sine inverse of x is what gives us that function. And the derivative of tan inverse of x gives us this function. So we're just working backwards from those. Okay. Now let me show you an example. Okay. This is a problem that we're going to get used to recognizing is when we have like the square root on the bottom, okay, there's just a number on top, and there's a function squared in the bottom. So if I had given you this problem before, don't write this down, you might have said u equals 1 minus 4x squared, because that is an inner function. Okay. So then du equals negative 8x dx. But we run into a problem. We have no x dx. Sure, I can bring the negative 8 over, but I got to have something to substitute in for my variables. I have a 1 dx, not an x dx. So I can't use this as my u substitution. All right, but if you notice up above, this looks very similar to 1 over the square root of 1 minus x squared. Okay. So what if I kind of did it that way? What if I made this kind of like my x squared? Well, what if I wrote it this way? 1 over the square root of 1 minus, instead of 4x squared, what if I said 2x the entire quantity squared? Is that not the same thing above? It's just I kind of undistributed it. The reason is because now, what if I let this quantity inside, what if I let this be u? So u is equal to 2x, and du is equal to 2 dx, and I can bring the 2 over. So what I'm left with is 1/2, when I bring the 2 on the outside as a half, the integral of 1 over the square root of 1 minus u squared. And I do know what that integral is. That integral is just equal to sine inverse of u, which in this case is 2x plus c. Okay. So we had to write it in the form that looked like that formula above by doing a little bit of u sub. All right, I only got a couple more. I'm going to be done. One over x squared plus 4. Okay. Here's the thing. This looks very, like you can't let u be x squared plus 4. We're going to run into the same issue as the last problem. But the goal is to write it something like this. Because this looks very similar to, go backwards. It looks very similar to the integral that gives you tan inverse, 1 over x squared plus 1. It's a little different. Okay? So what we got here is 1 over, the goal is to have x squared plus 1, something along those lines. Okay? So we're going to have to rewrite it to where we have a 1 here, a 1 here, and then some quantity squared, because then I can just do u sub. Right now we have a 4 there. That kind of complicates things. All right? Well, what if I factor out a 4 from the bottom to make it look this way? What if I do this? 1 over. What if I divide a 4 out? So I'll take a 4 out, then I'm left with actually 1/4 x squared plus 1. Do we agree that these two are not identical? It's just a 4 has been divided out. Okay. All right, so what I'm going to do first of all is I'm going to split this up. I'm going to go ahead and take this 1/4 kind of out. So I got 1/4 multiplied by 1 over 1/4 x squared plus 1. I just kind of took that out. Okay. All right, so I'm going to bring the 1/4 out, and I'm left with the integral of 1 over. Now, just like before, how can I rewrite this to where it's an entire quantity squared? Okay, what if I say, instead of 1/4 x squared, what if I say the entire thing squared is 1/2 x squared? Wouldn't you agree that this is similar to this? I just kind of undistributed as before. So what I did from the very beginning of the problem is I'm trying to get it in the form of 1 over something squared plus 1 so I can do u sub. I had a 4 there, so all I did was divide that 4 out and bring that constant out. I rewrote the 1/4 x squared as 1/2 x squared, and now I can do some u substitution. 1/2 dx. I can bring the 1/2 to the other side, and when I divide by 1/2, I got 2 du equals dx. So I can bring the 2 on the outside. I got 1/4 times 2. The integral of 1 over u squared plus 1 du. I should have been having a dx. Okay, and the integral of 1 over u squared plus 1, well, that's just tan inverse of u, and in this case, that u is 1/2 x plus c, and we have the 1/2 outside from 2 times 4. Okay? So there you go. Now, I taught you that because this happens a lot, to where we have 1 over x squared plus something other than 1, and I'm trying to get it to where it is 1. So that's kind of the math behind it. But if you do it enough, you start to notice a pattern for how this works. Let me teach you this pattern. I want you to add this to your list that we talked about today. So I'll kind of do it right here. If you do this enough, you're going to recognize a certain pattern. The integral of 1 over x squared plus 1. We'll stick with that. This is in a specific form. This is in a specific form of 1 over x squared plus a squared dx. Okay? This is an identity. This has its own integral, which is doing exactly tan inverse. But if you do it enough, you recognize that if you have this setup, you can integrate it a certain way. I'll go ahead and tell you the identity. The integral is going to end up being 1 over a 1 over a tan inverse of x over a plus c. Okay, so add this underneath your identity for tan inverse, because this is a special type of tan inverse. When it's not just +1, it's plus a squared. So in this example here, you can rewrite this as 1 over x squared. 4 is nothing more than 2 squared. Okay, so your a in this case is 2. So if you understand and can recognize the identity, this is equal to 1 over a, or 1 over 2, tan inverse of x over a, or x over 2, plus c. And again, this type of equation pops up so much with integration that it's worth making that note. And notice, we got the same answer as before, but now we just know the shortcut for that. Okay. So I'm going to go back here real quick. And I want you to make that note right here, that the integral of 1 over x squared plus a squared is equal to 1 over a tan inverse x over a plus c. So add that to your list. All right, last one. This is like number 13 on your worksheet from the other night, from last night, the night before. So if you can do this one, you'll be able to do number 13. All right, if you're given this problem, your initial thought would be to do this right here. You don't have to write this because it's not right. You would let the bottom be u because it's the more complicated one. And then you get 2x dx. Okay. Well, the 2 can come over. That's usually no problem. I think we're okay with that. But we're left with x dx. Well, here's the issue. Here's an x, here's a dx. But what about that plus 9? That plus 9 is married to that x. So I can't substitute that out. Well, there's a simple fix to problems like this. Okay? If you run into this issue right here, and you have like a plus 9 or plus number left over as an issue, well, it's a pretty quick fix. What if you split the fraction up? What if you split the top as x over x squared plus 9 and 9 over x squared plus 9? Those two are equivalent. Those two are equivalent. Okay? I just undid the fraction. Well, based off of our integration rules, I can separate this as 2 separate integrals and solve them as 2 separate rules. Okay. For the first part here, you can do that u substitution. You can let u be x squared plus 9, and du is 2x dx. Oops, sorry. 2x dx. And then I can bring the 2 over as a half, so I'm left with 1/2 the integral of x dx can now be substituted out as du, right? And x squared plus 9 can be substituted out as u. So I got 1 over u du. And that integration is nothing more than the absolute value, the ln, the absolute value of u, which is x squared plus 9. And if you notice this one right here, okay, well, I can go ahead and bring the 9 out as a constant. So I'm left with 9, the integral of 1 over x squared plus 9, or another way of saying that is x squared plus 3 squared. And we have a little nice rule for that. That's 1 over x squared plus a squared. So we know that integral is 9 times 1 over a, or 1 over 3, tan inverse of x over 3 plus c. That's the newest rule that we learned. And if you want to simplify as your final answer, you can say 1/2 ln absolute value, blah. 9 1/3 is 3 tan inverse x over 3 plus plus c. So with this integral here, we had to separate it and use two rules. First rule was a natural log. The second rule was a tan inverse. Okay. And remember the things to look out for. If you have a difference in power of 2 to 1, so like a difference of power of 1 from top to bottom there, it's going to be natural log. And if you have a difference in power of 2, so you may go from an x squared to no x, that's going to be tan inverse. So those are things that you can look out for. All right, and that does it. So you got some book work that I would like for us to work on in class. And in class tomorrow, I'm going to try my best to not spend the whole class just going over what the video lesson already says. So if you're watching this, you are a good student. Keep watching the videos, please. All right. Well, thanks, guys. Good luck, and we'll talk about this tomorrow.